Hello students! Let me ask you a simple question. Why don't lakes and rivers freeze completely solid in the winter? If they did, aquatic life would vanish. The answer lies in the anomalous expansion of water, and one of the most famous proofs of this phenomenon is Hope's experiment. In this classic demonstration, scientists show that water doesn't behave like ordinary substances between 0 and 4 degrees Celsius. Instead, it becomes densest at 4 degrees and expands below that. Let's see how Hope's experiment brings this mystery to life. Here's how the experiment is arranged. Imagine a tall, transparent glass jar filled with water from top to bottom. Two thermometers are placed inside, one at the bottom and one at the top. The entire jar is surrounded by a jacket of ice, so the water cools from the sides toward the center. Sometimes a gentle heat source is added to regulate the rate of cooling. As you can see in the diagram, this setup ensures we can watch how the temperature at different levels changes during cooling. Now, as cooling begins, both thermometers, top and bottom, show a steady fall in temperature. Water behaves normally above 4 degrees Celsius, it contracts as it cools, density increases, and the cooler, heavier water sinks downward. This convection circulation continues until the water near the bottom of the jar reaches 4 degrees Celsius. So far, everything looks ordinary, but then comes the surprise. Once the bottom water reaches 4 degrees Celsius, its density is maximum. Now, as cooling continues below 4 degrees, water begins to expand instead of contracting. Its density decreases, so this colder, lighter water floats upward. The thermometer at the top keeps falling towards 0 degrees, while the bottom thermometer stays fixed at 4 degrees. As shown in the diagram, the bottom remains at 4 degrees, the densest layer, while ice eventually forms only at the top surface.
So why does this happen? The answer lies in water's molecular structure. As the temperature drops below 4 degrees Celsius, hydrogen bonds arrange molecules into an open hexagonal pattern. This pattern increases the space between molecules, lowering the density. That's why ice, the solid form of water, floats on liquid water. The density temperature graph shows a clear peak at 4 degrees Celsius, proving water's unique anomaly.
Let's now see this anomaly with numbers. Suppose we take 1000 grams of water at 4 degrees Celsius. Since density equals 1 gram per cubic centimeter, its volume is 1000 cubic centimeters. At 0 degrees Celsius, density drops slightly to 0.9998 grams per cubic centimeter. Using the formula density equals mass divided by volume, we substitute 0.9998 equals 1000 divided by volume. Solving, volume equals 1000 divided by 0.9998, which gives 1000.2 cubic centimeters. So, the water has expanded by 0.2 cubic centimeters just by cooling from 4 degrees to 0, a tiny number in the lab, but in nature, on the scale of rivers and lakes, this effect is massive. So, what have we learned? Hope's experiment beautifully demonstrates water's anomalous expansion. Water cools normally down to 4 degrees, then expands as it cools further to 0. The bottom of lakes and rivers stays at 4 degrees, while the surface freezes, protecting aquatic life. The molecular cause is hydrogen bonding, which creates an open structure below 4 degrees. The consequence is life-saving. Lakes freeze top down, ice floats, and ecosystems survive harsh winters. So to sum up, Hope's experiment is not just a classroom demonstration, it's a powerful reminder of how a small anomaly in water's behavior sustains life on Earth.